Greetings everyone. Welcome back to Multivariable Calculus. We're still building up all of the tools that we need in order to start in our 3D exploration of functions. The next topic we need to talk about are different coordinate systems. Let's start with cylindrical coordinates. So just as the name suggests, these are coordinates that are based off of the idea of a typical cylinder. And remember, we've dealt with cylindrical graphs already, things that are sheets of one cross-sectional object. I'm talking about the old school version of a cylinder that you're used to thinking of, the can shape, right, of a cylinder. Cylindrical coordinates are based off of that idea. And it's really just an extension into 3-space of polar coordinates, right? It's an extension of polar coordinates into the third dimension. It works exactly the same as polar coordinates in the y-x plane, and all they're doing is bringing in the z coordinate with it. So normally in 3-space you'd have x, y, and z for your rectangular coordinates, and then when you convert into cylindrical, you'll have r, theta, and still z. So there actually is no conversion for z, okay? What you need to imagine is if you have, like a can or something like that, imagine being able to walk around the can, right? And then change the size of the can if you need to, as far as the girth, the radius of it, right? And then being able to walk up and down the side, okay? So like if I see a point in space, I can rotate to being right underneath of it, walk till I'm underneath of it, and then move up to it. That's cylindrical coordinates. And really the goal here is to just have another coordinate system for some of my applications later to convert into that still uses a radial type of thought process, okay? The XY plane is very commonly going to be where a lot of our domain values come from, or all of our domain values practically. And so being able to convert just the domain into a radial concept a lot of times will help later on with our derivatives and integrals. Okay, so to convert, all of the equations look just like polar coordinates, right? R cosine theta, R sine theta for x and y. And notice z is unchanged, okay? And vice versa. R squared equals x squared plus y squared, and tangent of theta is y over x. Again, that's the same conversions from polar. And you can see on the grid here, for the point right here, the z is the same. And instead of walking down the x-axis and parallel to the y-axis, all I'm doing is rotating. And remember, right-handed system, right? Right-handed system, look at the way the angle is rotating from x into y, and it points in the z direction, right? So that's still the exact same definition of theta that you were given back in a 2-dimensional rectangular. It rotates from the positive x-axis until it hits where your radius is, right? And then you walk out underneath the z, and then there's your z component, okay? So that's cylindrical coordinates. Let's do a couple of conversions and talk about regions and stuff. Okay, so we're going to convert the points here from rectangular 9, -2, 7. To convert that one into cylindrical, I'm going to need an r, a theta, and a z. Well, I've already got z, don't I? So it's still going to be 7 in the z. I just need to convert the x and the y now into the r and theta. Okay, well, don't forget that r is equal to, or comes out with r squared is equal to x squared plus y squared, like so. And I'm just going to square root both sides. So I can quickly find r by doing that calculation. That's going to be 81 plus 4 Square root of 85 would be my r. And don't forget, r can be negative. I took a square root there, and it typically would have the plus or minus with it. I'm choosing the positive one in this case because of the way the point is oriented, and I'm going to choose the appropriate theta to make sure that my r can stay positive, okay? If you're not sure what I'm talking about, go back to the talking about that we've talked about on polar coordinates in other classes, in my trig class and things like that. You'll remember that polar coordinates has multiple spots where a point can be oriented depending on whether you want r positive or theta. Not the point oriented, the coordinates can be different for the same point I'm making. Okay? Now, from the xy plane, 9, negative 2, I need to think about which quadrant that would have been in, right? So 9, positive x, but negative 2 on the y would put me in quadrant 4, right? Which means I'm expecting my theta right here to be some angle that's bigger than 270 but less than 360, or in radians bigger than 3 pi over 2, less than 2 pi, right? Or I could use the negative. Either way, same thing. But I'm going to use this equation right here. The tangent of theta is equal to y over x. Okay? So tangent of theta is equal to negative 2 over 9. Now be careful. My theta, I can have multiple choices here. And in my calculator, right, need to grab handy dandy time saver. In my calculator, I'm only going to punch in the inverse tangent of 2/9. I always do only the positives. Okay? So I have, let me put it in radians. Inverse tangent of 2/9. Not the negative 2/9. Because I'm going to get a reference angle. My reference angle is 0.218. Okay? Now, 0.218 is the reference angle. It's not my answer, because if I just do the 0.218, that's a quadrant 1, and tangent isn't negative there. I really want the quadrant 4 version, so 0.218 is the reference angle in quadrant 4. Just to give you a quick reminder, this is what I'm actually doing. I'm going to pick my theta like this, such that it's in quadrant 4, and this angle right here is the 0.218. So what does that mean? I'm going to do 2 pi minus this reference angle, and I get 6.06. radians. Okay? So I've just converted that point into cylindrical. Really what I did was I converted the xy into polar, right? It's no different than what you would have done in a trig class, or possibly even the calculus class before this. So really no difference. Okay, now what about converting this back into rectangular? I'm going to use the x and y formulas here for doing that conversion. I'm simply going to do r times cosine of the angle and r times sine of the angle to quickly convert this back into rectangular coordinates. And then, of course, my z component is still going to be the same, right? 1. So for the x component, I have 3 cosine 4.7, and I'm in radians, right? So 3 cosine 4.7 is going to give me negative 0. Let's just do 0.4. And I'm just going to hit up, change the cosine to a sine, and I'm getting negative 2.9997. Well, that's close enough for me just to put negative 3. Because if you were going to graph that, you would not be able to tell the difference between negative 2.9997 and -3, not on a graph. Okay? So conversions here work the same as converting from polar coordinates. Next, let's talk about sketching a region in cylindrical coordinates here. Okay? And the reason I want to talk about this is because you're accustomed to thinking in rectangular. And in rectangular, if I just give you x is between two numbers, y is between two numbers, z is between two numbers, all you're going to get is a rectangular solid, right? Not necessarily a cube, but it'll be rectangular. And if you're thinking in terms of cylindrical coordinates, you get a completely different object. Okay, and that might be something that would help one of our problems later. Okay, so let's see what kind of regions we typically get when we graph something in cylindrical. Don't say cylinders. It won't always, it'll be a type of cylinder, but it won't be necessarily the kind that you're thinking of. All right, so first, what I want you to realize is that if r is in between two numbers and neither one of them is 0, right? Typically the beginning one not 0, then we have what is called an annulus. Okay? An annulus is an object that is two concentric circles, and you're interested in the region in between them. I know what you're thinking. Donut. Do not mistake this with a donut. Okay? It's not round in the third dimension. It's flat, right? But it is, a circle with a hole cut in the middle of it, basically. So notice, r is between 3 and 4. That means my inner circle would have a radius of 3. That's the cutout. And then my outer circle would have a radius of 4. So it would be all of the points that are between a distance of 3 and 4 from the center of the grid. Okay, now remember that's two-dimensional. And theta, that's just an angle, right? Between 0 and pi. Let's think for a second. Between 0 and pi on the normal grid, right? That's the positive x-axis to the negative x-axis. And then z is between 0 and 2. That's where the cylinder part comes in. I'm going to just take the shape that I get and I'm going to pull it, extrude it up from the plane from z equals 0 to z equals 2. All right, let's draw it out. Let's get a grid going on here, a 3D grid. Okay. So here's my x-axis, here's my y-axis, here's my z-axis, and you'll notice that I drew the x-axis into the negative side of itself because I need that, right? I need to be able to rotate my theta between 0 and pi, which is going to require my x-axis to have both sides. Okay? Now, let's start with the annulus of my r here, between 3 and 4. If I were to measure 3 marks, let's go ahead and do that. Let's measure 3 marks in each direction on an axis that I need. So like that. And like that. While I'm at it, I'll go ahead and measure the couple of marks on the z-axis as well, since we'll need that also. I'll go ahead and put 4 marks, even though I don't need that many. All right. So let's start, like I said, with the annulus for r between 3 and 4, which of course I forgot to put mark number 4. I know, I didn't measure the last one. Oh no. Didn't measure the last one. Okay, so 3 is going to be a circle that goes through 3 on each of these axes, like this, right? Now notice I'm only drawing the semicircle between 0 and pi of an angle. Okay, next, 4. Right? So there's my flat annulus. Well, it's only half of one actually, right? It's the top half of one. And I'm interested in all of the R pieces in between those two, right? I'm not interested in anything in this region over here. All right, and then for my Z axis, I need to go from 0 to 2, okay? So to help myself, what I'm going to do is I'm going to draw something parallel to the x-axis, but I'm going to draw it at 2 on the z-axis. Okay, so I'm going to do my best to line up a parallel line with the x-axis here. Like that. And then same thing with the y-axis. I'm going to draw something parallel. Like so. Okay? And then I'm going to just line it up vertically in each point. So that would be here and here. See, I'm just lining up the points along the z-axis here. So that would be here and here, here, and here. Okay, I think I'm just about ready to get it. Let me draw the top one in blue so that we can tell the difference here, right? So I've got this little section here where it cuts off, and this is the section here where it's going to stop, and this is the intermediate section right here. Okay, so it's going to go like this, and then like this. Okay, and then of course they would be connected vertically like this, and then some of it should be dashed in the back, of course. This will be connected here, this will be connected here, like this, right? And then I'll be interested in this entire top region here, down to that bottom region over here. Okay, so it looks kind of like a C, right? Just going between the two parts of the x-axis and just stretching the little strip along the whole way. Okay, that's a cylindrical coordinate region for these particular numbers. So that's what you can expect whenever you want to convert something into cylindrical coordinates. I just wanted to briefly show you, as real as I could, what that region in cylindrical coordinates really looks like. And here it is. As you can see, it's half of an annulus, right? It's the right half on the xy plane, but also it has the depth from 0 to 2 in the z. Now let's convert some equations from rectangular into cylindrical. And this is actually where more of the applications are going to happen, is because you're going to have some surface in the 3D space that you need to describe in the cylindrical coordinate system. For derivatives, for integrals, especially some integrals later on, you're going to want to convert some of these things. And I have a couple of examples here of the ones you would probably want to, and then maybe some of the ones you wouldn't want to later on. But just so you'll get an idea of why we would do these conversions, right? Okay, so there are going to be some that are better for it. Anything that has the the cylindrical feel to it, where Z doesn't matter as much, and also where it has some sort of a center around one of the, especially the Z axis, is something that would do really well in cylindrical coordinates. X squared plus y squared equals 9, right? Now think for a second back to the last section when we were talking about cylindrical surfaces, right? Something that's missing a letter is going to be one of those surfaces. There's no Z here, so that means it's going to be a cylindrical surface, right? Okay, so I can convert this into cylindrical just by saying x squared plus y squared is r squared, and then taking the square root. I'm getting that r is equal to 3 for this guy, right? R is equal to 3 is the cylindrical coordinate equivalent of that equation. Okay? Next, z equals e to the negative x squared minus y squared. The first thing I would do with this one is I would factor out the negative. And I'm noticing that I'm getting that x squared plus y squared again. So I just have z equals e to the negative r squared, and that's where I would stop. Okay, so these are obviously equations that work really well moving into cylindrical coordinates, and these are a lot of the objects later on that you would probably use this application for. But what about things like planes, especially planes that are just some angle off of the center, nowhere near the origin even sometimes, and definitely don't have a cylindrical, round type of feel to them. It's going to feel real chunky in cylindrical. Now that's not saying you may not have to do this later. Some applications may call for it. This one probably is not going to be the one that you'll do as often though. So take a look. Here's what would happen. I'm going to get my z by itself first, and I'm going to convert my x and y. So that's going to be 2r cosine theta plus 7r sine theta. Because my x is r cosine theta and my y is r sine theta, I'm going to subtract the 10, and then it's going to be equal to z because I'll add the z over as well. About the most you could do is possibly factor an r out of here, but there's no r on the negative 10. Okay? So then this is pretty much where you're stuck at, converting into cylindrical coordinates. I've got my r theta and z now as my components there. Okay? So sometimes when you convert things it works out really nice. Other times it may not work out as nice. We also need to be able to convert the other way. Sometimes we may create an object that's easy to explain in a radial or cylindrical manner, and then I may want to see what it would look like in rectangular in case it's something that I can interact x and y and z. Okay, so for this one, I would start by not having 2 theta here, right? So to do that, I'm going to have to use my identity. Sine 2 theta is 2 sine theta cosine theta. And then I'm going to go ahead and just add this over to get it out of the way. So I'll have z squared plus 1 over here. For this guy right here, I'll probably want to split this up. Since it's r squared, I can rewrite this as r sine theta and r cosine theta like this. See, because it's r times r, right? I'll just take one of the r's and use the associative property to rewrite the multiplication this way. And so really what that's giving me is 2 times y times x. And let's see, then I would subtract the 1, and it's equal to z squared. And typically we like to have z by itself in these equations if I can. And of course you could follow through by doing the square root, but I'm not going to worry about that here because I don't want to lose any of my values with plus and minus arguments and things like that. This is a decent form of that equation. Okay? So just get used to using those formulas for converting points, but also converting equations of objects, because you'll be having surfaces in 3-space that you may want to represent in a different coordinate system. With that in mind, the 3 special cases of cylindrical equations come out when you have, and just like with any coordinate system, right? If you have just one variable equals a number. Like in rectangular, if you have just x equals a number, or just y equals a number, or just z equals a number, right? You get those planes that only hit that axis. Okay? So notice in cylindrical, the z equals a number is exactly the same as it would be in rectangular, right? Because if z equals a number, you're basically just at that height above the xy plane, no matter what coordinate system you're in. The only difference would be once you're at that z height, how would it get to the other points? By using r and theta instead of x and y is really the only difference. But they're all still there though. It's still all the same points in the plane. When r is equal to a number, right? Like this one right here. Notice it's x squared plus y squared equals 9. That's a circle on the xy plane. But remember, the z is still there. It just has to be parallel to it. So you get a cylinder, right? A circular one. And it extends up and down forever because z can take on any value, right? So when r equals a number from the cylindrical aspect, you're saying theta can be any angle and z can be any number. But r is constant. So it gets to that certain circular size for the r, the radius. And then it goes all the way around because theta can be any number. And then it goes forever up and forever down because z can be any number. If theta is given some value and said it has to be that constant, then what's happening is from the positive x-axis, you're rotating to some angle. And then you're saying, okay, but r can be anything. So r can be any positive and r can be any negative. It'll go forward and backward in a straight line, right? But it won't rotate at all because theta is not allowed. So you have this, but then also z can be any value, right? So you're taking that line and just saying, okay, z can be any value. So you get this vertical plane instead that goes through the origin and is an angle off of the x-axis, whatever size theta is. Now we need to discuss the other coordinate system that we'll be using this semester, this course series, and that's spherical coordinates. It's a system that it basically takes the idea of polar and cylindrical and makes it even more general as far as the using rotation to aim and a radial line to travel. Okay, so just like any other coordinate system, you need to have 3 coordinates. Okay, but this time 2 of the coordinates are going to be angular and then 1 will be radial. All right, so this is how that works. You start with your pointer pointing upward like this, okay? You rotate like this in the XY plane, right? You rotate your XY plane, not the plane itself, but you rotate in the XY plane first. That's your theta. Then you rotate another angle that we call phi, like this. From the upward position, it can go all the way to the downward, but not past it. It's a semicircle rotation from 0 to pi, can be anywhere in there. So let's say you want to go about here, right? So let's go through that again. I've rotated a theta and I rotate a phi. and then you travel radial in that direction toward any point. So notice that that can locate anything in the 3D system, because I could point in any planar direction. I can then point directly at the point, whether it's high or low from the plane, and then I can travel straight to it. So that's any point I can locate with spherical. So here's how the coordinate setups go. You have the point that you want to get to right here, okay? There's your z, x, and y axis. And what you're going to do is you'll calculate theta the same way you would for polar and cylindrical coordinates, okay? That theta hasn't changed. It's in a rotation from the x-axis going towards the positive y-axis, okay? So that's the exact same theta you're accustomed to. Here's the r that would have been in cylindrical and polar coordinates, okay? All of that stuff is still active, by the way, okay? You can use all of that stuff sort of as a stepping stone to get to spherical. From R and Z, right? The R is just in the plane, and Z is the component coming up. Those two form a right triangle, and that's where I get my rho coordinate from. Rho is the squiggly sideways looking P. It's actually the Greek letter rho. It's like their version of R. Makes sense, right? Radial. Okay. It makes a right triangle where rho is the hypotenuse. Okay. And then the angle phi is coming off of the positive z-axis. It's coming off of the positive z-axis. So from up here downward. Okay. So the angle's up here, not actually inside of the right triangle that I've drawn between z and r. Okay. If you prefer, you can draw the radial component at the top and use the z-axis as your z, and then the angle would be inside of it. Or you can use the fact that the z component over here and the z-axis are parallel. That's the arrows I drew. They're parallel. So you can use alternate interior angles here, and it's still the same phi inside the top of your right triangle. Either way, what you should be noticing is that rho squared is z squared plus r squared, right? Pythagorean theorem. But we already know that r squared is x squared plus y squared. So rho squared is z squared plus x squared plus y squared. That's one of your conversion formulas. Okay? Also, from the right triangle here, you should notice that r is the opposite side to the angle phi, which means that r would be equal to rho sine phi. And z, being the adjacent to phi, is going to be rho cosine phi. Okay? That's one of your direct conversion formulas right here. This one is useful by itself if you're converting from cylindrical to spherical, or vice versa, spherical back to cylindrical. Okay? However, since x is equal to r times cosine theta and y is equal to r times sine theta, then from this statement right here you can get that x is rho sine phi times cosine theta, because that's r cosine theta. And then again, r sine theta. Y is rho sine phi sine theta. Okay? It seems like a lot of big formulas there, but if you build it, right, using the right triangle and make sense out of it and then use it a few times, it'll stick to you pretty well. Okay? Now when we do coordinates, we typically do x, y, z, right? In spherical coordinates, I'm going to be using rho theta phi. Okay? Rho theta phi. Of course, any of the variable can take on any value, but the standard form of spherical coordinates, rho is going to be positive, right? Some positive distance. Again, it could be negative. It just means to go in the other direction. But we typically don't need that. And that's for the reason of the angles here. Theta is 0 to 2 pi like it always has been. It can go all the way around the x and y plane, right? Phi does not need to be anything smaller than 0 or bigger than pi. Phi is this angle, right? the angle doing this, okay? And it doesn't need to go anywhere other than from straight up all the way to straight down. Because think about it, I can already rotate theta like this. I can already do that. So any point I can do this with, just, you know, one semicircle here, I can get anywhere I need to because theta already covers that whole plane. So I just need to do this for my z dimension, okay? So phi is typically only between 0 and pi, and rho will typically only be positive because that's all we typically need. Can they take on those other values? Yes, of course, because when we solve things, all manner of different solutions can happen. But what's going to occur after you get a negative or a weird outside value than what I'm saying here is you'll just find a way to convert it back into this standard form. We typically like theta to be between 0 and 2 pi. I typically want phi to be between 0 and pi, and I want rho to be positive. Okay? Let's convert some points. 5, 4, negative 2 in rectangular. All right? Well, remember, in rectangular, what that means is that I've got 5 and 4, right? In the xy plane will be somewhere in the plane. And then I'll have to go down in the z, negative 2. Okay? So it'll be the xy plane and it'll be below it, right? Okay. So to get to that location, I'm going to want to find my theta, right? My rotate out to it. And then I'm also going to want to find a phi, which is going to rotate downward, right? Because here's my xy plane, right? I'm going to have my theta go out to it, and then it's below the xy plane. So I'm going to want to do this. And then I'll go out to it, okay? Well, let's just do some calculations. Rho is going to be equal to the square root of 25 plus 16 plus 4, right? That's just using this right here to get my distance that I'm going to have to go. And that's my first component of my other coordinate system. So we've got square root of 45. I guess we can simplify that. Let's do 3 square root of 5, right? Okay. That's my rho. Okay, what about theta? Well, tangent of theta is still equal to y over x. Remember, that's active. That has not changed. Still the same. Because it's the same theta whether you're in cylindrical or spherical. Okay? And 5, 4 is in the first quadrant. So I don't need to do any kooky tactics here. I'm simply going to do the inverse tangent of 4 over 5. In radians, I'm getting 0.675, right? For inverse tangent of 4 over 5. So 0.675 for theta. If you wanted to do that in degrees, you could also have put the 38.7 degrees. That would work also. Okay. And then what about the last angle, the phi? Where do I have to rotate there, right? Well, I'll use this right here. Z is equal to rho cosine phi, right? Okay. So I've got negative 2 is equal to rho is 3 square root of 5 cosine phi. Since I've already figured out what rho is, I can easily get my phi from that. And I want you to notice now that I'm going to get something bigger than pi over 2. And I should, because I'm starting from up here and I'm rotating down below the xy plane, right? Because the z is negative. Okay, so for my phi, I'll be punching up the arc cosine, the inverse cosine of negative 2 over 3 square root of 5. It's okay to do that with inverse cosine because Anybody? Because inverse cosine is defined only for first and second quadrants in the xy plane. And that's exactly the kind of angle that phi is always going to be, either a first quadrant for the top or a second quadrant for the bottom. Okay? So again, since I did radians before, I'll do radians now. I'm doing inverse cosine of -2 over 3 square root of 5, or you know, it would be easier to just type the square root of 45. Okay, 1.874. Or I guess if you wanted to do degrees, right? 3 square root of 5, I think we said 38.7 degrees. And then what's this one in degrees? 107.3 degrees, right? Remember, we typically like to do things in radians, though. Okay, so this would be the coordinates in spherical, where the last two are the angles in radians. Okay, so then how do I go back from spherical into rectangular? No problem. I've got these three equations already set up and ready to go. I just need to punch them into the calculator, really. There's literally no written work for going from spherical here because I have these lovely conversion factors there, right? So I'm just going to type them in. I've got square root of 2 sine of, now be careful, this is theta and phi, right? So sine of pi over 4 cosine of pi over 3. Okay. So let me type that in. I'll write it out first. Square root of 2 sine pi over 4 cosine pi over 3. Y is going to be square root of 2 sine pi over 4 sine pi over 3. And z is just going to be square root of 2 cosine of pi over 4. Right? That's my conversions there. Okay. So let's punch and crunch. Now, of course, we know these, right? Sine of pi over 4, cosine pi over 3, so on and so on. Some of these might come out to be pretty nice. This is square root of 2 over 2, right? Times square root of 2. That's going to give me 2 over 2, which is 1. So I've got cosine of pi over 3. Let's write them out. Square root of 2, square root of 2 over 2. And cosine of pi over 3 is a half, right? Because that's just 60 degrees. Next, I've got square root of 2, square root of 2 over 2. And sine of pi over 3 is square root of 3 over 2. And then over here, I've got square root of 2 times square root of 2 over 2. All right. So in rectangular coordinates, this one would be 1/2 square root of 3 over 2 and 1. All right, so just like before with the cylindrical, it helps to see what's going on if you can sketch a region in this particular coordinate system. So again, I'm giving the three different variables, each in some number range, and we see what kind of object we get. Now remember, in cylindrical, when r was in between two values, I had an annulus, which is two concentric circles. Rho works very similarly, just in a 3D fashion, right? Because rho can point in all directions like that. And if it's between 1 and 3, what you need to imagine is a sphere inside of another sphere, right? An annuloid, if you will. Instead of an annulus, the flat kind, right? An annuloid, where I have a hollow ball in the middle of a larger one, and I'm interested in all the points in between them. right? Okay. Then I need to interpret the angles so that I know exactly which sections of those balls that I'll be cutting out, right? So theta is between pi over 4 and pi over 2. Okay, well, in the xy plane, if this is my x-axis, right, theta is going to rotate to pi over 4, which is halfway, and then to pi over 2, which is the y-axis. So we're looking at the top half of the first quadrant, right? The pi over 4 to pi over 2 would just be this half of that quadrant in 2 space. Then phi is 0 to pi over 4. So 0 is the z-axis. And then pi over 4 is going to be halfway down from the z-axis, right? Pointing outward half of a quadrant downward. Okay, so here we go. Let's put some grid here. Here's my x-axis, here's my y-axis, here's my z. Okay. I want to rotate the theta to halfway, right? This will be to pi over 4. And of course, pi over 2 would be the whole thing. So remember, we're going to be interested in this whole section, okay? But not in the plane. I'm just showing you that that's the range of my theta angle here. Okay, so then on top of that, I'm going to rotate my phi angle from 0 to pi over 4. So phi equals 0 is the z-axis. That's here, right? That's phi equals 0. And then to phi equals pi over 4 is here. Okay? And that's right above this radial line. Then I have to rotate it around like this to the theta equals pi over 2. So that's going to also be out to here. And it's going to be around like this. And then I have to do rho from 1 to 3. So if rho equals 1 is about right here-ish, and then 3 might be somewhere about right here-ish, imagine pieces of spheres, okay? It's going to feel round here first, and then it's going to be the other way underneath. So I'm going to have something that looks like this. And then something that's like this. Okay, so it's going to be radial here, and then it's going to be round on the top, like that. Okay, and it's going to come from the same point on the z-axis here. So it's going to feel pointy here, and then it's going to be outward like that. Okay, graphing is a process, don't forget. So it's going to be, imagine a piece of a sphere there, right? These are radial. Like this. Like this. Okay? So then it would be, at the bottom, it would be the same thing. It's going to be round here and round here as well. So it's this little section in between two spheres. And I have a cutout in a circular pattern because of the way the angles work, right? I have at the bottom, I would be cutting out the bottom sphere, and I would have all the region up to the other sphere. So imagine, two round shapes, trapping pieces in between them like that. But it's not entire spheres. It's only a little cutout of a sphere in a radial fashion. So since they're both coming from the z-axis, they're gonna be sort of like pie slices off of the top of the sphere there. Okay? All right, so that's how you can sketch a region in spherical coordinates. All right? Let's get some examples converting some equations.
Again, like before, I really just wanted to show you what that region in spherical coordinates look like. Like I was trying to describe before, it's the area, the volume really, all the region in between two spheres. As you can see, this is a cutout of a sphere down here at the bottom, and another cutout of a sphere at the top, and it has that triangular but rounded triangular look to it. So it's just the cutout between the two spheres there is all.
So let's finish up with a few more conversions and special situations in spherical coordinates, right? So as before, some objects are really good in certain coordinate systems and they're really bad in others, and vice versa, right? Planes tend not to be good in anything other than rectangular as far as equations go, right? So if I'm going to convert this into something that's in spherical, I've got my x, y, and z, and really there's no better way to convert this other than just start plugging in things. So I'll have 2 rho sine phi cosine theta plus 7 rho sine phi sine theta minus rho cosine phi equals 10, right? Something like that. And of course, one thing I can do is I can factor out the rho and then divide by the pieces, right? So I could get something where rho is isolated, and I would be left with 10 over 2 sine phi cosine theta plus 7 sine phi sine theta minus cosine phi. And that's just a Yokohama mess, right? That's definitely not a nice way that I would want to represent an object, especially not a plane that could easily be talked about with a normal vector and being, you know, perpendicular in just rectangular form. So only when absolutely necessary, right? Okay, next. X squared plus y squared equals z squared, right? If you remember, that's a cone because I could also write it as x squared plus y squared minus z squared equals 0. And remember, when one of them is negative and you have equals 0, that was the cone shape, right? So you can imagine something that goes through the origin like this, right? That kind of shape, where this is the origin here. Okay? My z-axis, x-axis, y-axis there. So then let's convert this into spherical. I'm going to start by adding z squared to both sides. So that gives me 2z squared on that side, right? Now x squared plus y squared plus z squared is rho squared, and z squared is rho squared cosine squared phi, right? Because z is rho cosine phi. I can divide both sides by rho squared. Be careful. What I'm actually doing is moving this thing over and factoring it out, because you don't want to divide by 0, and rho is 0 at the origin, but it has the same result. Basically, what's happening here is that I'm going to be able to show that 1/2 is equal to cosine squared phi, right? Just by using some division and factoring. And what this means is phi is equal to whatever the inverse cosine of the square root of 1/2 is, plus or minus square root of 1/2, right? Plus or minus square root of 1/2. Now, square root of 1/2 is square root of 2 over 2, right? Which means I'm getting two different answers here. I'm either getting pi over 4 for the positive one, or 3 pi over 4 for the negative one, okay? Now think about why this makes sense. Phi equals a number, which actually we're going to talk about right here, is one of the special equations. If phi equals a number, I get a cone because phi is this angle, right? So I say lock into pi over 4. But I can still do as much radial as I want, so the cone will keep going outward. And I'm locked at this angle, but I'm not locking theta, right? Theta can still go all the way around at this straight line. You get a cone, okay? And of course, since I'm getting two different solutions here, it's doing the top and the bottom cones, right? Because 3 pi over 4 would be past halfway. Okay, so then next, this one right here, x squared plus y squared plus z squared. Remember, that's the equation of a sphere. And then the only other thing I have is this plus 8y. If I were going to leave this in rectangular, don't forget I would put the y squared and the 8y together. I would complete the square, add a number to both sides in order to do that. It would give me a radius over here of 4, because you get 16, right? And basically what you're seeing is that it's a sphere that's been shifted along just the y-axis, right? So I've got a sphere on the y-axis, centered around the y-axis, and it's hitting the origin and a further point on the y-axis, basically, right? But I'm going to leave it in its current form so that I can convert it into spherical. X squared plus y squared plus z squared is rho squared. And 8 times y is 8 rho sine phi sine theta is equal to 0. If I factor out a rho and notice that I can't have rho equals 0, then what I'm going to have is that rho has to be equal to negative 8 sine phi sine theta, right? I just factor out a rho, and then I've got two solutions. Either rho is 0 or rho is equal to this. Rho equals 0 would just make it, a point. So this is my equation in spherical right here. Okay? Now, rho equals 6 cosecant phi. That's already in spherical. I'm going to convert it back into rectangular. And you'll want to do this sometimes to see if, hey, what does that actually look like, right? You may be interested in what this actually looks like. And don't forget, the whole idea here is supposed to be we're writing surfaces in other coordinate systems to make some of our math easier. And yes, I do mean easier. The conversions do help in some later derivatives and integral applications, okay? So to do this one, what I'm going to do is I'm going to multiply both sides by sine phi. And since cosecant and sine are reciprocals when they're of the same angle, this is just 1. So 6 times 1, right? And then rho sine phi. We had a thing for that one. What was that one? That was r is equal to 6, right? So basically I've converted it into cylindrical here, right? Square both sides. R squared equals 36, right? So I've got x squared plus y squared is equal to 36 in rectangular. So r equal to 6 in cylindrical is the same thing as x squared plus y squared equals 36 in rectangular. And what shape is that? There's no z, remember? So it's a cylindrical surface, and it's circular. So you're actually getting that circular sphere here. R equals 6, right, in cylindrical. So whenever you're using just cosecant of phi in spherical coordinates, you're actually getting a cylinder there. Okay? And then again, to talk about the other two special equations here, this one should make sense to you because it's just the radius is equal to a number constant. So in other words, from the origin in all directions, right, it's all the same number. So you're going to get a sphere if you just have rho equals a number. If you have theta equals a number, the only difference between this and cylindrical is the fact that in spherical, my other coordinates are limited by phi, right? Phi is typically only allowed to be 0 to pi. So if I lock in a theta, I can't go behind me, right? Because we want rho to be positive and phi only to be the 0 to pi. So in this case, you're only getting a vertical half plane because I lock in a theta and all I can do is this, right? I can only look straight ahead and rho will go outward and I can only do the angles here to here, okay? And we already saw about the half cone on that one. So I hope this has helped you understand the other coordinate systems that we'll need. Stay tuned, we'll start actual multivariable functions next.